So welcome to talk about JVM things, which you may know about. Hopefully you know some of this stuff. It has been interesting talking about these things, how often you forget what you rely on. So I will cover stuff and you'll probably have heard of them. Some of the stuff in here you may not have thought about, but some of the features you'd have heard about, just probably not used them. So my name is Steve Poole. I work for a company called Cernotype. I've been doing JVMs since they were this big. In fact, I was working at IBM when we started to bring Java in. So back in 95 or 96 it was. So I have had the fun of working with JVMs since they were tiny. And I've done a bunch of other stuff as well. But being a JVM engineer and delivering JVMs and JDKs for 20 odd years taught me a lot. So yes, so I work for this company. Who's anybody seen the logo? Know who we are? Maybe a little bit of you. Yeah. As a Java developer, you'll know us more because we're the guys behind Maven Central. We've been running Maven Central since the beginning, right? So Maven Central is going to turn up in the talk a little bit, but really this is JVM stuff. So we're going to talk about security features. But the thing we're not going to talk about is we're not going to talk about the security manager, which is good because it's been deprecated. This is one of those things that came in the early days of Java because it was seen like a good idea to do. It was badly implemented and it just got in the way because it was not the right solution. So finally, it's gone. But then pretty much, I don't think anybody ever used it. We're not going to talk about some of the obvious replacements. People are bubbling around about how do we solve the same problem. We're not going to talk about that. No, we're going to look at the intrinsics. So when you look at JVM design and you go way back, there are lots of good words about the intent. And you can see this is about integrity and confidentiality, okay? Security has always been in everybody's mind when we code JVMs. It's always been there. And it comes out in the design, okay? Now, before I talk more about the design, what I need to talk about is why this is important. Because, like all good stories, you have to have bad guys. Because without bad guys, there's no real reason to have security. And unfortunately, right now, bad guys are on the rise. And the scale of the problem that we as a community face, as the world faces, is tremendous. So if I'm going to put it in a nutshell, I have one slide to put it in a nutshell. The amount of money that cybercrime costs the world, that's amount of money they take from you, or how much money you have to spend to deal with the attacks, if you sum it all up, it's estimated to be about $9 trillion. And that's such a large amount of money, it's almost impossible to get your head around it. But if you look at it like this, as if you imagined it was GDP, if cybercrime was a country, it would be the third largest country in the world. And this is growing at about 56% per year. It's been growing like that since early 20s. 2016, it was about 500 billion, and it's just going up. This is the problem we have. There are a lot more bad guys out there, and JVM, your applications, is a target vehicle just like everybody else's. Now, they have multiple ways of getting in. We'll talk about how they can get in. And there's sort of two things that go on, and you've got to get your head around this. They're going to try and attack your systems, and we'll look at what they could do from a JVM point of view and see how well you're protected. But they also try and attack the open source projects that you consume, or those dependencies that you download. Okay? They try and attack those as well. So there are two things going on here, and we're going to look at the elements and the protections. From a bad guy point of view, because developers worldwide aren't very good at being secure, it makes it really easy. So now what you have is this idea that the open source that's in that makes up your application, 90% of an application, you didn't write it, right? You picked frameworks, you picked runtimes, you picked open source stuff. And all the stuff that you depend on, including the JVM, are potential attack vectors. Because if they can sneak the stuff in, they don't have to attack your system. It's already there. So this is a big vector. This is one of the primary vectors in most space, especially in the Java space, right? Okay. It's not the only thing, but you need to understand that every piece of code that you download is potentially a bad vector for stuff getting in. Okay. And where for quite a long time these bad guys would sort of just be trying to find vulnerabilities, something get reported. We found a security problem, and they go, great, we're going to exploit it. And we used to have time to deal with those exploits. Somebody would tell you there's a vulnerability, you had some time to fix it. Nowadays, we're in a different mode. Nowadays, we're in a world of exploit first. So by the time you see a major vulnerability hit the streets and somebody says to you, we have to update, you have zero time. Because if it's announced, it's already been exploited. So the stakes are high. Every way that things could get in, they're going to try, and every protection that's available, you should be looking at, will it make a difference? So we're here to talk about JVMs, because that's a particular part of this whole puzzle. And we want to look at attack vectors. How do they get in? Right, well, you have to start with a picture of what's a JVM, right? And if you've thought about it at all, you will probably have spotted some of these words. So up the top is your code, application code, and all the Java dependencies that you pick, fine. And at the bottom, the OS that you're running on, the hardware you're running on. And so obviously the JVM's job is to map those together. And tucked away inside of this, and we'll talk a little about these things, are other things. So like there's classes that you don't write, the system classes. There's the JVM, the binary, which has got stuff in it. So it's got a compiler. It's got its own native code. It's got places for user native code. It's got JNI, which is a support boundary between the JVM and the native code, right? So there are bits and pieces that could, in theory, be used to attack the JVM, right? And then it's got loading classes from local disks, remote disks, okay? So there's quite a few elements in a JVM. And so when you start talking about attack vectors, the first one which comes up, which we're going to deal with straight away, is well, you've got one of these and you've got it on the web. How are they going to attack you? And then you get, well, maybe they're going to have a go at the communication side, right? Maybe they're going to attack your communications processes. Can they get in to the protocols? Can they affect that stuff? Right. Well, we're going to write that one off pretty quickly, because if there's one thing that you can get from the JVM, from the Oracle guys, is that we implement the best protocols as quickly as possible. There's no hanging around. So yes, sometimes protocols have design flaws, and sometimes implementations have design flaws, have coding flaws, but you're not looking at old you're looking at old protocols, and we're definitely looking at supporting the latest. And there's a lot of them. You can go have the links, but when we look at it and go, what's the likelihood of somebody being able to compromise the JVM through playing around with the communications protocols? Pretty low. If there was a intrinsic design problem in that protocol, which there have been in the past, what everybody does is the world gets off it and we move to something else. So we can discount that one, right? So that bit, that's fine. So there are other places though. How about where the JVM meets the operating system? What about the bad guys being able to compromise those? Can they compromise the configuration? What about environmental variables and things? Can they get at those pieces? Does the JVM give you any protection from the bad guys playing around with the configuration that you've created? The command line things, what can it do in that space? Well, the basic answer is it's not seen as a JVM problem. The JVM has to trust the environment that it's running in, so it has to trust that you have that under control. Now, one thing I want to bust, because this comes often, is there's this concept that if the bad guys can get access to a file on the file system through whatever vulnerability they exploit, which is obviously a way of being able to change your config, the myth is that if they can access one file system, they could access anything. And the simple answer to that's not true. There are lots of vulnerabilities that have come through where the ability of the bad guys to get to the file system is to get to a file, right? So if you hear about vulnerabilities that give access to the file system, don't go, all bets are off. It's like, no, you could still have that vulnerability and it could still be used to compromise you, but it's not necessarily in a very large way. But it can get to possibly the config files, right? And can it get to environmental variables? Maybe. Whatever it gets to, it's your problem, right? The JVM, as you can imagine, has nothing in there. And there are things that could be done by the bad guys, like turning off verification, etc., that would have potentially detrimental effects on the security of your JVM. Right, so communications protocol safe, command lines not so much. So the environment is your problem. Now between these two, we've got the JVM. So you have to start thinking then from a JVM point of view, look at JVM design and go, what's available to be played with? What could bad guys do? So you get sort of three ideas. So we know JVMs create code. So there are sort of like, could we play with the bytecode? So could we play with the bytecode dynamically? Could we change the bytecode on disk? Can we get into the memory? Can we attack the memory in some way? And then what about just can we load in remote code? Right. So those are sort of the three elements that when you're looking at attacking a JVM that will come up, because they're pretty much what you'd see on almost any system. It's like, can I screw with the memory? Can I load code? Can I play with the code? Can I make it do other things? Okay, so for us to answer these questions, we have to take a dip into what a JVM is. So you can read the words, but ultimately, if you think about it, it's a mapping layer. It takes the environment that you run, and it provides all the translations so that that machine code, that bytecode that you created, will run anywhere. That's the objective. Now the detail, there's a lot of detail. Because you think about all the different combinations of hardware and operating system, threading models, windowing systems, you name it, there are so many of those, and then you have each of the combinations. So like networking as well. How does the processor work? So all these things. So you can see that it's quite a complicated challenge for us to take all of that variability and present it to you in a way that you get the same results whether you're running your Java code on one slice through this or another slice through this. Okay? So we obviously don't want to have that mess to deal with. Right? We want to abstract it. So we want to structure it down. So when you look at a JVM, when you start boiling it down, and you start looking at the specifications that are coming out, because we have to have specifications, we have to have ways of communicating and the correct behavior because of all those complexities. Right? So we're starting to boil down. We've taken off the Java code, the Java applications, because that's not, ironically, it's not what JVM cares about, is it? It doesn't care about Java code in that way. So you start to see some of the words that we've used already. So that's cool. We've got specs that start talking about these elements. The weird thing is, this is too complicated. So a lot of that, what you might think would be specified, isn't. And in fact, the model that we use starts to get actually even simpler than that. The model, the specifications that we use. Okay, so we need a memory model. We want a model of the CPU, so we have a stack. We need a threading model, because we've got to do synchronization and stuff like that. And then we want ways of going from JVM to operating system. Right? So that could be the spec. That could be what gets written down about behavior. But as you'll see, even this is too much. So a JVM specification, the bit that does all the heavy work, as far as a specification, is this. We have a JVM that understands about a stack, what a stack computer is. We have a JVM that has no idea about threading. It has an idea of looking, but has no idea of threading. And it has no idea of memory. All it knows about is object references. So that's the core. Now, whether this is, we can say this was by design, or whether it was by accident, this base really helps keep the JVMs secure, because we have this level of defined behavior, and then a lot of implicit behavior that is defined in other ways. Okay? And when I say, other ways, it's the magic. So let's look at some of this stuff. So because we've got a small model, a very simple model of a JVM, that gives us a whole bunch of protection. Right? So you look at the first level of protection, is just the whole idea of what a JVM is. It's so simple. If it's simple, it's hard to compromise. So many processors out there, if you've ever written any assembler, you have lots of registers for keeping data in, keeping references to objects, places on disk. The JVM has one. It's called the program counter. It just tells the program which is the next instruction. And you can't use it. It is not addressable by machine code. It changes based on the instructions you execute. So it can't be changed. Other programming languages, other models, other environments, you can move the program pointer around that pointer, and you can say, don't sit here, sit over there. Whereas in Java, you ask somebody to sit somewhere, and the pointer then moves to the next seat. And you can't control it. Okay? So you can't move it. There's no addressing of memory, because memory doesn't exist. It's just references to objects and what's on the stack. Okay? You can't break out of it. There's no way to get out of this very, very tiny state model, this stack machine, to any of the things that you might want to have fun with, right? You can't say, hey, I'm running an ARM processor, let's do some magic. Can't do any of that. You are constrained to just those few things, right? Now, the bits that aren't specified, they are specified, but they're specified in different ways. If you ever feel like tracking things down, it's always fun to go look at the specifications that we all live with and figure out where the rules are. And quite often, the people, the place where things are defined aren't necessarily where you expect, right? So look at that. So memory management. There is no specification for memory. There's no specification for garbage collection. It does what it's supposed to do, and that's it. So if there's no spec, if there's no way of influencing it, then the bad guys can't get at it directly, right? It's like threading, right? There was only one place in threading where there was a leaky sort of abstraction, because we had this thing called thread locals, because real threads have connections to things like database connections. And so they were slightly available for compromise. But now when we're going to have virtual threads, there's no relationship between the virtual thread and the real thread. Okay, so you can't break out. Bad guys can't write code that breaks out. So you're safe, right? Which is awesome. Right. And then the JIT. The thing that is unspecified that takes the bytecode and converts it into machine code. It is unspecified. It's unchangeable. You can't play with it. And in fact, its behavior, the behavior of a JIT, adds more benefits. Because JITs are dynamic, they do things like allocate storage dynamically, right, in this memory space that isn't specified. And so the bad guys, if they're trying to find something on the heap, externally trying to access the heap, and they're trying to find some location, that gets hard because objects move around. GC moves objects in unspecified ways. So the bad guy is trying to look at your memory space and going, where's the password stored? Well, that's really hard, because there's no simple way of getting access to it, to identifying where it is. Right? And also, with the JIT, because the JIT is turning bytecode into machine code, this is not a simple activity. It's a very complicated activity based on profiling your application, what's happening in the heap, all sorts of stuff. And so the code that gets created is different every time. So even if there were weaknesses in physical hardware CPUs, and you could conceptually imagine that the translation of bytecode to machine code might expose one of those, there's no way of forcing it, because you have no way of making the JIT do what you want, because it makes up its own mind, because it's been doing it's all this unspecified activity to give you the performance you need. And then there are other bits and pieces, like if you're an architecture and the JIT understands about different memory types, like read-only or read-write stuff, it can make use of those. Unspecified performance. That is, second line of defense. Now the third line is the bytecode itself. It's very, very simple, and it just operates on those object references and on the stack, right? So you can't play with it, right? It's very simple, and we put a whole bunch of effort into proving. So there's a thing called verification, and verification looks at this bytecode when it loads off the disk, and it makes some assertions about whether this is valid. And it's pretty good now at being able to spot invalid code. Now it was done, the verifier was there for a long time just to stop the JITs and things crashing. Because if you get a JIT to just compile random bytecode that it hasn't checked out, it might generate crap machine code and things could fail. So part of the verification was to prevent that happening. But also, we're trying to prove that you can't escape from the bytecode. So the verifier, which runs all the time when you're loading code, which you don't notice, is there to give you another level of safety. No. So it sort of pre-executes the bytecode. And when I say that, it doesn't even touch the bytecode. Verification, bytecode disappears very quickly. When you load a class with a VM, the very first thing that happens in that class is it's converted from bytecode to an internal representation, right? And then verification takes place, because stack machines are really hard. and they're very poor performance. And so most of the JITs use the bytecode as a sort of model of what your application is trying to do, and they create their own internal representation, which is nothing like a stack machine, and verify that. Right. More classes, more things, like class loaders. Now, class loaders used to be a big thing. You used to read, I mean, if you were in the Java days, in the early days, there'd be all sorts of conversations about class loaders. You can have systems. Anybody here using OSGI? Yeah, because OSGI likes class loaders, right? What's the idea of a class loader? To encapsulate the code, to apply extra rules. I can have a class loader that I can trust. I can have a class loader that's for loading, untrusted code, and I can keep them segregated. I can stop my system being polluted by bad code or code I don't trust. That was the idea. It sort of works. I don't think we really make that much use of it. Nowadays we have 3 major class loaders, the system class, the extension class, and the bootstrap. They have different privileges, but most of the time you probably don't notice these things. What the bad guys will try and do is see if they can compromise the physical disk. So they could try and compromise your command line, but also can they get at the classes that are on disk? Right. And of course, if they can compromise one of these things, then you could be in a world of pain. Now, when I look at the JVM, I would often say it's pretty robust. Right? The design is such that it's hard for bad guys to break out. There are no escape vectors, except for one. And that's, well, anybody remember this? Log4j, anyone? Yeah. Wow, Log4j. Okay, Log4Shell came out, and this is a quick description of Log4Shell. Tucked away in here was these things called reference objects. And a reference object is an implementation. It's got linked to a JVM, but basically it's a sort of class loader that you can say to this reference object, any class that I reference after me comes from this URL. So if I can get one of these reference objects into the system, then I can do bad things because I can pull in any arbitrary code. I don't have to worry about what code's on your disk. I can just download whatever code I can lay my hands on. And that was at the root of why Log4Shell was so bad, because that was pinning the JNDI stuff that was added. Okay, and I want to talk a bit more about serialization in a minute. Well, in fact, now. But the horrible thing. Let's talk about this. Serialization. I say how well the JVM is constructed. There is this gaping hole, and it's called serialization. And I have to say, I actually wrote some of the code for it when we added it. Java didn't have serialization when it came out, but it became very obvious very, very quickly that we need some way to get data in and out of the heap. And so serialization was written before bad guys existed, or at least as far as the Java team were concerned. And it was a very nice, simple design, and it's gone everywhere. It's very performant because we made it very performant. Right, and anywhere you can find object input stream. So I went to Google last year and said object input GitHub and said how many are there, and it told me you can't avoid this. Object input stream is everywhere because it is the way that you serialize data and you send it around. Okay, and it's bad. Right. So here's why it's bad. This table is a table form of the data stream that you might get if you serialize something. Okay, so this sort of represents this class at the top there, which has one field. Okay, and it has a field called hello, and it's a string. Right, and you can see down here that this is a data stream, and at some point you get there and it says field name hello, and then it says class name Java lang string, and then down it here says the value. Right? What you have to get your head around is is that the relationship between the name of the field in the object and the data that's following, there is no relationship. What Java serialization says is, I know where I'm going to put it. It's called hello, and I know what I'm going to put. There is no reference to what's in the class. Okay? Right? Yeah, I think I've done that. Yeah. So that means that the little tables could be data, right? And the data that's coming in the stream can be anything. It could be hello, which is the normal case. It could be an array. It could be an int. It's the same moral thing as seeing something like this in the code, right? Now you're going to say, okay, some of these things don't compile, right? And that's right. Because one of the things that bad guys could do is, rather than put a literal in there, they could force a class. They could just say instantiate an object. And when it fails, you get an error message like this. And it says, it cannot assign instance. So serialization allows for the arbitrary instantiation of objects and can fill the data in with arbitrary data. Right? And all it has to do is get into one of those streams. Doesn't matter what your code does. It can use that break to start its own chains. Okay? Yeah. It's horrible. And you just can't escape, right? Implement serializable is the thing you put in your class to opt in, and it's everywhere. Right? So what are the bad guys trying to do? They're just gonna, all they have to do is one way in, and then they can build these chains. And they can have this object create, and this, and part of its instantiation creates another one, creates another one, creates another one, creates another one. And if they can get that into your stream, then they can do whatever they want. And if you have a reference object, like I showed you in there, then they don't have to try and build attacks using the code that's on your class path. They can load whatever code they want. Okay? And if you think that sounds hard, it is hard, but this is what's called a gadget chain. So you can see at the top it's got object input stream read object, which is where things start, and at the bottom is runtime exec, because that's what they're trying to get to. Yes? And that's the sequence. So they've got to work out how to make one call the other, call the other, call the other. And you're going to sit and say, hey, that's really hard. And it is, right? But it's okay, because there are tools out there to help you do it. Right? Don't ever think that bad guys are not funded or stupid. And unfortunately, some of these tools get written by people who are just having fun. Right. So, what can we do about serialization? We have some defenses. It's not the greatest for sure. And in fact, for many people, it's just too clunky. So there is a configuration you can set, and you can say things like what you're allowed to be in that stream and what will not to be allowed in that stream. Okay. It's not really great. It's a big, big stick to try and deal with things. Okay. Now 17 made it a little bit better because they started putting in, giving you the ability to do wildcards and stuff like that, and giving you whitelists and blacklists and things like that. But you have to do all the hard work. And the problem with this is, a lot of the time you don't even know what codes you're actually you're loading until you've done it. Right? And then you have to start updating these things. And so it's painful. Right? This is great for serialization attacks. It's a defense that you have to work at. It's certainly not a great story. Okay. Now, there are other things you could do. You could look at it differently, and you could say, hey, why don't you use modularity? You know that thing that's been in Java forever? Well, for a few years, right? Because attackers mostly can only load the code that's visible to them. By having class loaders or modules, you reduce the attack vector because there's less classes for them to build. Some of those chains would fail if you're using modules, because some of the objects would be in different modules which weren't accessible. Okay? Pretty much modularity is at the root of what the Java guys want to do. Right? Always moving forward, they always think about Java modules. I know many people don't use them, but that's how they think. Right? And then you can use modules with things like JLink, so you can actually have a smaller footprint, and therefore there's no code to be exploited at all because it's been taken out. Okay, that's cool. Right. If you don't want to use modules, you can use sealed classes. Sealed classes gives you some protection because you can say, if I load any classes that have this space, whatever you put, will come from this jar. And if the VM tries to load classes that match that from a different jar, you'll get a failure. So they're worth looking into. Mm-hmm. And then if you still want to use serialization, then I would encourage you to look at different design patterns and not try and serialize big fat objects, but spend time with maybe things like data records, because they're just state. And that does make it a little bit easier. Right. What else could you do? You can compile stuff to native. That definitely shuts the door on a lot of things because you're going straight to native. Most of the Java code is gone unless you're having any sort of support for extra reflection. Right. You do lose a bunch of performance, but it's a thought that maybe if you compile, you'll get better protection. Okay. So from a JVM point of view, it's intrinsically sort of designed to be safe, but there are a few holes, right? So I'd say in general, it's a good place. I've looked at other runtimes over the years, and you can see lots of places where bad things can happen because they've designed it poorly. But there are some secret weapons that we can add on top of this. The first one is Maven Central, which I know probably all of you use, right? Because malware, which is predominantly a fabulous tool for the bad guys, the way that they get malware into the system, into this open source, is via all sorts of interesting attacks. Right? And I don't have time to go through them, but believe me, there's lots of ways for them to compromise the code that you download. But if you go to Maven Central, so Maven Central has two levels of protection. One is by design, and one is what Sonatype brings to it. By design, you cannot publish code to Maven Central without proving that you own the domain. Right? And I'll talk about that in a second. And the other thing is that every piece of code that ever gets pushed up to Maven Central goes through all of Sonatype's security software, because that's our business. So you get all that for free. We've only ever found one piece of malware in the whole lifetime of Maven Central, because mostly people don't create malware using Java. But that was maybe changing. So the types of attack that you can see the bad guys doing, typo squatting, where when you type in the name of the package in your dependencies, you spell it wrong. And unfortunately, rather than it saying can't find it, because the bad guys have registered something with the typo, that you get their code rather than the code you're expecting. That's mostly reduced because you have to own the domain, and if you want to register a domain for every typo that you can think, you can imagine that's costly, so that doesn't really happen. Dependency confusion is one that doesn't happen. Dependency confusion is where let's say example. So I publish something and I publish it at version 1. And then somebody else publishes the same name but uses a higher version, maybe 9999. And then I can publish version 2, and I can say, yeah, I've updated it. And all my users go get latest. They don't get my code. They get the code that somebody else published with a very high release version number. That is not a Java thing, because you can't do that with Maven Central. But other programming languages, Node and Python and stuff like that, have that problem. Okay? So we don't have that. The other two, open source repo attacks, which is is a common way of trying to compromise your code, is way downstream. Not much we can do about that. That's a common problem. And build tools attacks, and that's getting into your Jenkins server and just adding malware in at the last stage type thing. Again, we have no protection over that. That's totally in your hands. Which leads me to the last one here. Secret weapon number 2 for Java security is you. And you're not doing a good job. So log4j. This is a chart, and you can go to this URL, and you can go, this is live. 35% of all the downloads for log4j in the last week were for vulnerable versions. Now that number goes up and down by a few percent, but it's pretty consistent, right? It goes, what it tells us is 20 to 30% of the people using Java, downloading these things, don't realize that somewhere in their system they are downloading a vulnerable version, right? And the problem is, this is the NSA's, this is last year, it's still pretty current. They listed out the top vulnerabilities that the Chinese Republic are using against us. And what's number 1? Log4j. So I would encourage you to spend some time thinking about the code that you download and going back to first principles and checking what you're actually downloading and see if you can figure out whether you're one of the 33% that are downloading log4j unexpectedly. Okay? Because it turns out that in general, as a developer, when we choose code, 96% of the time, this is a Java story, you pick something for which there is a better, less vulnerable version available. And once you've picked it, and it's in your software supply chain, all that ever happens after that is it gets bumped by version. You know, you find a vulnerability, you improve it. If you guys spent just a little bit more time and you started thinking a little bit more about the contents of that thing that you're downloading, you would not have log4j, and you'd be just a little bit better off security-wise, and you'd probably spend less time patching. And the good news is that though I can say to you, just go off and find this stuff and make decisions, and you might go, I don't know how to do that, we, industry, are working hard on figuring out how to quantify it. So keep an eye out for this. This one's things that we've got on Maven Central. You can go read all the rules, but what we're trying to do is figure out what information we can give you so that when you make that choice, you pick a better choice, not just because it's got no vulnerabilities today, but also because the people providing it know how to do software engineering, so they won't have a vulnerability tomorrow. So there we are. Whirlwind tour. I hope you can see, I hope, giving you a taste that the JVM is pretty solid. Right? I hope you've made you realize that serialization is still the bad guy, still around there. And I hope you realize that you have to do things differently because the world has changed and you're on the front line. So every time you pick a new piece of code, or if you go look at the stuff that's in your dependency tree now, go just make a little bit more effort to figure out whether you've got the right one. That's it. Thank you. Right. I have this thing. Right, here we go. Have Maven's, I'll put it full screen. Have Maven Central considered taking down versions of packages with known critical vulnerabilities? I could have paid you to ask that because I get asked that all the time. The simple answer is no, we don't do that because the vulnerability is a vulnerability. It depends on circumstances. So you need to know you're downloading it, but you may be downloading it. You may be a researcher downloading it for various reasons. So if we were to stop you downloading it, then people would moan at us because they're going, I'm still using it. You know, there may be people have legitimate reasons for downloading Log4j, and they've got it in a firewall environment and they can't be attacked. Maybe they know what they're doing. So we never actually do that. As I said, the only thing we'll take down is absolute definite malware. Is that it? Oh no. If not serialization, what a better alternative for data exchange? Good question. What do you do if you don't like serialization? Well, there's two answers. One is you can go use something else like, I don't know, was it Eclipse Store now? Xstream. I've got a fast serialization alternative, really, really fast, and that's cool. The problem is that you have to be able to control the use of serialization, and so much of this is happening in the frameworks that you use, and there's no way to get at it. You've got to find every place that object input stream is used in the code that you're using and get them to change. And there is no real credible alternative because everything else you do, converting it to data or JSON or whatever, hits performance. So unfortunately, right now, it's not a good story. You can write code to stop your code being exploited, and you can go read about this, but it's a lot of effort to make it happen. Right, next one. Are there any plan to sandbox serialization code? That's a good question. I don't know. The way, if you talk to the Oracle guys, what you'll get is everybody agrees that this was a really bad idea, but nobody wants to rush into something new. They'd rather spend, they're looking for a better solution that we can encompass all the code. So I don't know. So sandboxing would be cool. In theory, that would work. I don't know. So I will go find out because I'm interested myself. Okay. That's it. Aha. Listen, thank you very much for listening. What can I say? Thank you for coming to JCON.